Thank you very much. I'm very glad to give a lecture in your seminar. So I'm particularly grateful to Stephen and to Julien for the invitation. Now I'm going to lecture on joint work with Junia and Sao. And somehow the main theme of this lecture would be, if you want, in just one word, well, 2 words, extension theorems or twisted canonical forms. And so what you will see in the following minutes will be this is somehow the plan of my lecture. And so let's start very elementary with the following, with a few observations concerning the canonical forms as follows. So we have a smooth and proper family of holomorphic manifolds such that each fiber xt is scalar. And the central fiber will be our X, will play a special role in what will follow. And our main hero today would be, as always, the canonical bundle, so the top power of the cotangent bundle of the central fiber. And then, so let's look at the Hodge numbers of fiber xt, HPQ. So the space of PQ forms, which are D-bar closed, modulo D-bar exact ones. And then one important result about this dimension here is that the function which T associates these Hodge numbers, HPQ fxt, is upper semi-continuous. That is to say, it can jump, but only upwards, right? And then on the other hand, Hodge theory tells us that the sum of all those numbers, HPQ, of xt, for indices P and Q, which adds up to a fixed number K. Now, this one is a topological invariant. In other words, it's independent of T. Now, if we join these 2 dots together, we conclude that actually the function is not only upper semi-continuous, but actually is constant. Okay, as we know, as I'm sure all of you know from very basic Hodge theory. So in particular, for indices P, Q equals to N0, so N is the dimension of the fiber, then we know that this dimension, the dimension of canonical forms, the holomorphic forms, holomorphic section of the canonical bundle, this dimension, it doesn't jump, it's constant for all T over the base here. And then with a little help from deformation theory, we can reinterpret this condition by saying that given any section of the canonical bundle, so on the central fiber of the family, it admits an extension in the following sense. So there is a global section of the canonical, there's a holomorphic section of the canonical of the global family here, whose restriction to the central fiber is our S. So restriction here, the notation is sometimes confusing. So let me just explain it. So this one is the top form on the total space, right? So it can be written as dt wedge eta, at least locally. But then, so of course, eta here is not unique, but its restriction to X is unique. So, those forms, even they are defined locally, they glue together, they piece together, and they give us a section here in the canonical bundle of the central fiber. And this would be our restriction as tilde divided by dt. Okay? So in this sense, this in this sense, every holomorphic canonical section, so section of the Kx, extends to the global family. Is the restriction of some holomorphic form here. Fine. So, but now we are getting a little bit more greedy. So let's consider a holomorphic line bundle. In other words, a twist, because what would life be without a little twist here and there? So, and in general, the function of the dimension of this space, canonical of xt tensored, here I noted with additively, plus L restricted to ST. Now, this dimension is still upper semi-continuous, but there are simple examples showing that in general, is not constant. So what does it say for us is that sometimes, so there are some special points on the base D, on the unit disk here, D, and some section in some holomorphic canonical section with values in L, which is not the restriction of some global object. Okay, so because of the presence of this twist, well, some special fibers have some additional holomorphic objects which don't come in family. And then, so one technique in analysis which will give us a sufficient condition for which this will happen, so that this function will be constant, is the notion of a metric. So I will very quickly review now the notion of Hermitian metric of a line bundle. Again, I apologize for the experts. I'm sure most of you encountered this notion here. So what is it about? We have this holomorphic line bundle, which is, of course, locally trivial. Locally, all the bounders, they look the same, right? U times C. And then a metric is simply defined as follows. So on this trivial bundle, we have a privileged metric, so a way of measuring the vectors, which is the absolute value square. And then we want something which looks like that, but which is global. So, and the condition is that, so a metric for the line bundle here will be the usual absolute value square, but multiplied with some function, some positive function, which we call a weight, in such a way that we get the global object. That is to say, measuring a vector in a fiber of L, it's independent of alpha. Okay, that's exactly what I wrote here. Now, once we have such an object, of course, you can construct it locally by absolute value square and then by a partition of unit. But locally, once we have such an object, we have a few other operators which are induced. Yeah, okay. So first of all, due to the holomorphic structure here, we have a d-bar operator. That is to say, if I'm giving myself a smooth section of L, I can take the d-bar exactly as we take the d-bar of a function. And this makes sense globally because of the holomorphic structure here. But then there is no natural d prime on a holomorphic line bundle. On the contrary, as soon as we fix a metric, we do have a natural 1-0 derivative, which is given by the so-called chain connection. And if you fix those weight functions for the metric, then locally the operator here looks exactly like the untwisted one, the usual 1-0 d prime. And there is a correction, which is the wedge with the weight function here, phi alpha, the derivative of phi alpha. Now, if you wonder where this formula is coming from, as L, a holomorphic line bundle, admits a natural d bar operator, if I take L bar, that is to say, I conjugate the transition functions that we have here, so I will get an anti-holomorphic line bundle, that one will have a natural d operator. Now, the metric is exactly identifying L conjugate with the dual of L. And then when you look at this isomorphism given by the metric, the resulting operator is exactly this one. Okay, so that's precisely the chain connection. Now, there is another object that we associate with the metric, and this is the so-called curvature form. So it's the Hessian of the weights, right? So this is multiplied with the appropriate constant here, I over pi. This will give us the chain class of the line bundle. Now, okay, so this was a quick review of the notion of a metric and some objects which are associated with connection and curvature. And then, so like I said, what you see in all textbooks in complex differential geometry is that, okay, a metric, well, we simply take the absolute value square and we take a partition of unit. But what you should see is the following a very important example. How do we get a metric of the line bounded L here? By, if you have at hand some bunch of holomorphic sections. Well, then we simply define the phi alpha, the weight function here, is 1 over m, so those are the sections of m times n. So this is again a notation for L tensor m. So 1 over m log of the sum of the fi squares, where fi square is fi here is the holomorphic function corresponding to the section Si via this trivialization. Okay, so those are global objects, and then the phi alphas here verify the right transition property. So they glue together exactly as they should to give us a metric on L. Moreover, this is not just some metric, it has this property that the Hessian here, that is to say I times the curvature, is semi-positive as a 1-1 form. Of course, it can happen that those sections, they have a common zeros, and then this function here will be identically minus infinity, right? But then we can still define, give a meaning of this IDD bar of phi, not as a form, but as a so-called as a current, right, in a weak sense. And this is an important remark. For example, if we only have one section, then IDD bar of log of absolute value of f square is simply the current of integration over the zero set. Okay, so it's, the curvature now becomes a current. And in general, if we have, if the weights here are no longer smooth as they used to be in the Hermitian case, but just some functions which are locally integrable, well, we can still define this object here, IDD bar of phi alpha. It's just that it will not be a 1-1 form anymore, but a current, right? And the curvature, that's exactly what it becomes, a 1-1 current. And we say in this case here that H is a singular metric. Fine. So now, so like I said here on this slide, what I want to, the message I want to send is that this kind of object will help us to understand, well, it will give us some sufficient criteria for sections to extend. And this is what you will see on the next slide. So this is a very, very famous and important result, which they start with Osawa Takegoshi long ago. Many of you are not around. And people still continue refining it, and the version which is somehow closest to what I want to say next is the following. So we have, as before, Keller family. Actually, here the hypothesis is that the total space X itself is a Keller manifold, not only the fibers are Keller. And we have a line bundle together with a metric on X, and a section, canonical section with values in L on the central fiber of this family. Now, we assume two things. One is that the curvature form is semi-positive on the total space. And then we also assume that the section that we have here is L2. So with respect to this metric, so this is of course automatic if phi L, if the metric is smooth. But so in this theorem, we allow the metric to be singular. And then this condition here means to start with that the weight is not identically minus infinity on the central fiber. And moreover, the zeros of U, they compensate the eventual poles of phi L. If you have in mind the example that I gave with the log of the sum of the square of the sections, you will see what I mean here. Okay, so semi-positive on the total space and compatibility between zeros of U and the singularities of phi L. And then the conclusion is fantastic. That is to say, we get an extension in canonical of the global family twisted with L, so such that the restriction is our initial section, and together with a very basically optimal estimate, that is to say the L2 norm of U here of the extension is bounded by a constant times the L2 norm of the section of the central fiber. And here the constant, it will not play a role today, but it's actually universal. It can be taken to be pi if this is the unit disk. So it's completely independent of the section of everything. Okay, so that's a universal constant here. Fine, so this is really a famous result. It had many applications in complex geometry. But okay, so it does the job. Okay, so give us a criteria under which the sections on the central fiber here extend. And we have a bonus here, the estimate. Now I would like to move on to some result of the same time, but in this setting, the section is defined not only on the central fiber, but on some infinitesimal neighborhood of the central fiber. That is to say, the section of this shape here. Okay. And then, of course, we have a projection map between fk plus 1 and fk. So simply you restrict to an infinitesimal neighborhood of a smaller order. And then the question would be, okay, so this result here extends sections from the central fiber to the whole. When do we have, under which conditions, a section here in fk can be lifted to a deeper infinitesimal neighborhood? Okay, so here we don't pretend to extend it globally to x, but only to have it a little bit more holomorphic, so to speak. And then the result here was proved by Tsao, Odemae, Matsumura in 2016. Now the hypothesis is the same. So we have a Keller family and the line boundary here on X, together with a section of this fk. So this means, if you want, that okay. So the hypothesis is the same. So that is to say, the curvature should be semi-positive on the total space. And then, so since U is a section here, we know that the d bar of U is 0 up to this order. Okay, so U admits a smooth extension such that this is happening. That's not a hypothesis. But then the hypothesis in this theorem is that the form here, lambda k, is L2 with respect to this metric on the total space. And then this section U of fk extends to X. That is to say, there is a holomorphic section in K plus L, such that if we truncate this section at order K, that's exactly our UK here. Fine. So, and then here one remark is that for this extension here, we don't have any estimates. We don't know how large this the extension can be, and this is really a problem. Would be really it's an important problem to find some estimable extension, like it was the case in the Osawa-Takegoshi theorem. Fine. So now, after this preparation, let me come to the result I would like to discuss, one of the main results. So we have the same setup as before, with a section of the K plus L defined over a thick infinitesimal neighborhood of order K. But here, L, the twisting bundle, is the multiple of canonical itself. So n minus 1 times kx. And then, the notation we already fixed. L is the restriction of beautiful L to the central fiber. And then on this L, we don't have any, this time we don't have any privileged metric global, but we take the metric which is induced by this section restricted to the central fiber. Okay, so the weight is exactly like this, m-1 divided by m times the log of the holomorphic function square. Okay, so corresponding to this. So this defines a metric on the restriction of this bundle to the central fiber of our fibration. And then so another hypothesis is that we have some extension, let's say smooth SK, such that if I write d bar of SK as a multiple of some form lambda k, so again, this is just due to the fact that S is the holomorphic section here in this sheaf. But the hypothesis star here is that this lambda k restricted to the central fiber is L2. Okay, so this is a N1 form, which is L2 with respect to the Kähler metric on X here, and especially the weights induced by the section itself. Okay, so in this result, the section plays, if you want, two roles. It is the object to be extended, and it defines the L2 condition here. And then under these circumstances, we can extend S one step further. That is to say, we can find some section S hat such that we get d bar of S hat is tk plus 2 times lambda k. Okay, so it's more holomorphic than the initial one. Okay, so so if you want, is parallel to the result I presented before of Zhao, Demai, and Matsumura, except that we don't have any metric, any privileged metric on this bundle, which was assumed in the previous result. And the L2 conditions are similar. Okay, so this theorem, if you want, somehow fits in the L2 framework, like this. Of course, given that we only have a metric on the central fiber, we can only perform the extension at the infinitesimal level, like that. Of course, we also have a more general result involving some abstract line bundle here, but let's concentrate on this one because it's more natural and makes the connection with the motivation, which is the following. Now, as the motivation, I put here a very important conjecture by Yum-Tong Siu, which is the following. So, given a Kähler family over the unit disk and a section of n times kx, so-called pluricanonical section, then S extends to as a pluricanonical section to the whole space. Okay, so this is the conjecture by Siu, still around. I mean, the conjecture since 20 years, and somehow, why is this conjecture important? Well, in the first place, it was solved by Siu in 2002, but the hypothesis is that X, this P is a projective family, and is crucial for the so-called BCHM. That is to say, showing that given any projective manifold, the canonical algebra is of finite type. So now let me explain the real motivation of these extension theorems. Very often in the projective world, one acts by induction, by using hyperplane sections or restriction to lower dimensional case. And then for lower dimensional case, one already understands something by induction, and then one tries to get back to the initial setting, and this is exactly why we need those extension theorems. So the conjecture of Siu is used in a very, very clever way by these people to show the finiteness of the canonical ring, which was a very important problem in birational geometry. Now, in order for you to have an idea why this hypothesis is here, let me just tell you that the proof in the projective case of the fact that the pluricanonical section extends, well, relies on the properties of those linear series, that is to say, multiples of the canonical, twisted with some ample line boundary. Okay, so, and since in general on a Keller space we don't have any ample line boundary, so that the proof is completely out. So we cannot use any of the beautiful ideas there. Now, for the Keller families, a very nice paper was written by Levin, Mark Levin in 1983. And the idea there was exactly this, to somehow replace this boundary A by extending little by little to deeper and deeper infinitesimal neighborhoods. And then somehow this was what got us started in our main theorem, somehow trying to solve this conjecture, of course, by using infinitesimal extension as a substitute for the absence of this boundary A. Okay, so again, let me just advertise here, stress one more time about a little bit more about this problem. It's really important because people believe that somehow the solution should bring some new techniques in the field, and also the proof in the projective case uses some infinite process. One has to take a limit. That is to say, one uses analysis, the art of taking limits. And here, in the Keller case, it is expected the proof to proceed in only a finite number of steps. So this would be very, very important. Anyway, so for the rest of the proof, what I will try to do would be for the rest of the time, I will try to discuss the proof of this theorem, see what are the main techniques, and accidentally, one of the main techniques has some application to the so-called injectivity theorems. So let's see how we go about it. So remember that we started with a smooth section such that the d bar is a multiple of e to the k plus 1, that is to say the function that we have, times some lambda k here, which is smooth. And then let's consider the restriction of this N1 form to the central fiber. And then the problem to solve can be very easily formulated in terms of this restriction here. That is to say, this form, small lambda k, is the d bar closed, as you can see from this equation here and the definition. But then what we have to show is that lambda is a d bar exact. Okay, so it's a classical cohomological problem. So lambda k is an N1 form with values in this guy, in this multiple, n-1 times kx. Of course, in general, when we try to solve these kind of problems, we have some positivity in the twisting boundary here. Now it's not the case, right? We only have our section S, so this is what we will use. And so as a first step in showing that lambda k is a d bar exact, well, we will try to compute this lambda k. So the claim is the following, is that lambda k on the central fiber can be written as d bar alpha plus d prime beta, where alpha is an n0 form, beta is an n-1 with values in L. So again, L is this multiple of the canonical. And the coefficients are of this form, the coefficients of alpha and beta, of the form smooth function divided by S to the n. So S was the restriction of this smooth section to the central fiber, right? Holomorphic section. And so you see, if we forget about this pole here, for example, if this capital N equals to 0, then we are done, right? Because Hodge theory tells us that we will help us to conclude. We have this one, which is D prime exact and the D bar closed, so must be D bar closed, right? But of course, there's no reason to, as you will see from the proof, there's no reason to think that the coefficients are so nice. People call these forms alpha and beta with coefficients like this semi-meromorphic, so they are smooth divided by some holomorphic section. So let's see, how do we go about this claim? What we will do is try to take the derivative with respect to t. So we have to decrease the power of t here and then restrict to the central fiber. Of course, we have to do that in intrinsic manner, right? We are on a global manifold, so we cannot just take the derivative with respect to t like that. So let's see, what are the intrinsic objects which are needed? In the first place, this section, although only smooth, but still we can mimic the definition of the Chern connection and use it in order to define this operator D prime, which locally is exactly, so we copy the formula from the Chern connection 1,0 part. It was the logarithmic derivative of the section multiplied with the appropriate multiple here. And then we also need the vector field, which looks like d over dt, and locally d over dt plus something which is vertical, right? So of course such a vector field exists. The d bar of psi, by the way, is exactly the Codera-Spencer class of our family. And then with these two objects, d prime and our vector field, this would be our d over dt, the Lie derivative with respect to this vector field, which is for us d prime of the contraction with the vector field. So this is operator acting on n plus 1 q forms with respect to with values in L, with and the target is the same. Well, here is not quite exact because we have some zeros here in fk, so it's not well defined, but you will see it's sufficiently well defined for us. In any case, the important thing is a global operator like that. And then, so let's see how this works when we are trying to apply to this equation. Well, when we do, we take the contraction with the vector field and take the derivative. Here we will get k plus 1 to the k times lambda k plus t times k plus 1, t to the power k plus 1, excuse me, times something which is meromorphic. But the main point is that here I have a higher power than here. Okay, so the right-hand side is clear. Now, what do we get on the left-hand side? Well, if you look at the operators that you have to commute, of course, one part of it will be d bar commuting with contraction and the derivative, which is the d bar of the Lie derivative of this. The other one, some component must come because of this vector field is only smooth and not holomorphic. It's exactly this. And then a third term, which arises because of the commuting d bar and d prime. And that's the curvature, which I will not write it because, again, it will be always some multiple of t times something which is meromorphic. So as a result, after applying the Lie derivative to this equation here, what we'll get? We will get d bar of the Lie derivative of our smooth section plus d prime of the contraction with the d bar psi here will be lambda k multiplied to this t to a smaller power plus some meromorphic term times that t to the power k plus 1. Okay, so we see that there is good news and the bad news. Let's start with the good one, which is that we were able to decrease the power of t here. And then the bad one is that here we had a nice d bar of sk on the left-hand side, but now we trade it with a d bar of something plus d prime of something else. And which is more complicated than this one. But then still, there is another good news is that if we iterate this process, so we take the Lie derivative for this equation here, then we will not get anything more complicated than that. It will always be d bar plus d prime, the image of d bar and d prime. Okay, and the remark is that when we apply d bar of xi, we contract this with our holomorphic form with values in L. This is multiple of dt, right? So this is a form of type n-1, 1. But the still is a multiple of dt because of the shape of this vector xi. And then when we take the Lie derivative of the d prime of such an object, we get d prime of dt, which some other form here. Okay, the exact expression of this rho 1 is easy to determine as a function of rho, but then it's ugly and it's not useful for what I will discuss next. The point is that when we iterate here, we'll have the same shape. So after k plus 1 derivatives, we simply got our lambda k times some positive multiple, and will be d bar alpha plus d prime beta. And then so again, as you see here, the fact that you get some meromorphic coefficients is due to this operator d prime, right? In order to take the derivative in an intrinsic manner, we only have this operator here, which is singular. Fine, but okay, so this is our lambda k. Now, like I said, the poles that we get, for alpha and beta are rather complicated. So smooth divided by some power of s which we don't control. And now we will use the L2 hypothesis that we have for this lambda k. So our hypothesis is that lambda k square divided by s to this power is finite on the central fiber. So for example, if s equals to 0 is smooth, then this condition is void, right? So it's always satisfied. But then, of course, the zero loci of holomorphic sections can be very complicating. So this means that the coefficients of lambda k are vanished enough in order to compensate what we have here at the denominator. So now s equals to 0 is not so like I said, we may have singular components, and in order to interpret this condition, we consider a log resolution of this of the divisor of s. And then we write the inverse image of the divisor as well, the support. We will have two parts. So those, the E will be those which will appear with coefficient 1, and the F's will have a coefficient between 0 and 1. You will see in a second. So the inverse image of lambda k. So this will be a N1 form with values in E plus L. So where the E will be exactly this, and L will be some line boundary which contains effective divisor, so delta I Fi with a delta I rationals and in between 0 and 1. Okay, so then for this boundary L, we have a nice metric which is exactly given by this Q divisor here. And then, if we look at the L2 condition and we interpret it properly, what we see is that we will get an equation like that on x hat. That is to say, once we put everything in simple normal crossing in transversal, and then now let's change the notation. So from now on we are in a simple normal crossing case, and then here I will reformulate the problem. So we have alpha and beta, which are of this type with values in the line boundary L, which appeared before, and log poles along E, such that lambda divided by this section of E corresponding to E is in the image of D bar and D prime. Okay, so for the moment, alpha and beta, they don't have necessarily poles which are logarithmic along E. On the top of it, they also have poles along the singularities of the metric here in L. But the claim here is that we can reduce the situation more and get new alpha and betas in such a way that this is satisfied. So let's see how we do that. So let's assume that we have just the one component here in E, and that we don't have anything in F. So in this case, let's take a finite cover of our X, such that E is given by the vanishing of the first coordinate. And then let's consider this vector field, which consists of piecing together the vector fields which are tangent to E1. Okay, the so-called local logarithmic tangent fields to E1. And then consider this new form alpha 1, which is alpha plus some multiple of the D prime of the contraction of V1 with alpha, where D prime is the Chern connection here. And the number n here is the pole order of alpha along E1. Now, if you do the calculations here, what you will see is that for this new form, alpha 1, the pole order is smaller. Okay, so we replace alpha with alpha 1, which has a smaller order pole, and D prime of something. But then we can commute D bar and D prime, because the curvature is 0 in the complement of E. And then so little by little we improve the poles of alpha, and then we use this equation to improve the poles of beta. Okay, so that's what we do. So if you want, this is just a global manner of saying that if I have dz divided by z square is the differential of -1 over z, right? So we can improve the poles if we add the derivative of something, and then we arrange a little bit the terms. So we do, like I said, similar manipulation with this form of beta here. And the important facts that these two operators commute in the complement of the poles here. And of course that the D prime square is 0. So now let's reformulate our problem to sum up after these reductions. So even if, let's say, we forget everything about what we happened so far, and let's look at this. So we have a smooth and D bar closed N1 form on X with values in E plus L. E is the sum of hypersurfaces in X, simple normal crossing, and L has a metric which looks like that, delta I log Fi square. And then, so again, E plus the singularities of this metric is transversal, simple normal crossing. And we also have that lambda divided by SE. So lambda divided by SE, this will be a section, a meromorphic section in K plus L, right? So this one can be written as D bar alpha plus D prime beta in the complement of E with alpha and beta log forms. And then the conclusion is that lambda is D bar exact. Okay, so it's like that's exactly what we still have to prove. And then, so here, what I will do next for you will be to comment on what are the main tools which are needed in order to prove this sort of result. And then, so this looks very much like, if we forget about E and the singularities here, this looks like a DD bar lemma, right? So of course, Hodge theory will play a role, but it's a version of the usual Hodge theory. And then also what comes into play at some point is the properties of currents induced by forms with log poles. Okay, so let's see what we have here. Now, about the Hodge decomposition, what I would like to point out next is the following. So we have a compact Keller manifold and a simple normal crossing divisor like that. Okay, so this is the setup. And then for corresponding to this divisor and to any order that you can imagine here, M, then we have we can introduce the notion of a metric with conic singularities along this divisor, which is quasi-isometric with this model metric. So those are the equations of y locally, and then the rest is the rest of the terms is like in a Euclidean case. So dci bar, this is the so-called conic part. And then we consider also a twist LHL, such that the metric is given by some multiple times the equations of the divisor here. Now, the only thing I want from this multiple is that it's rational, and the M, the order here, is divisible enough so that M times delta I is integer. Fine. So then the curvature can be written as a multiple of the current of integration coming from here plus some smooth part. And then the notion that comes into play is a generalization of the so-called orbifold forms. So let's say that the L-valued PQ form is smooth in conic sense if the inverse image of alpha divided by W to the power M times delta is smooth, where pi here is the local uniformization, right? So we take the Zi is Wi to the M for the equations here. So the pullback of this metric will become Euclidean, right? And then there is this additional contribution which comes from the metric of L. Okay, so without any delta here, this would be simply orbifold differential form. But then we have to take into account the fact that those forms are L valued, and then what we impose is this condition. Okay. So and then with this notion we have the analog of the Hodge decomposition. That is to say, the L2 forms with values in L which are L2, they decompose exactly like in the usual case. Also, the smooth forms, the forms which are smooth in conic sense, they can be written as so the kernel of the Laplace plus the image of the Laplace. Okay, so we have the perfect analog of the Hodge decomposition in this setting. And then, so I will only say to you that the proof is based on the usual result, because what we do is to analyze the situation by using these local ramified covers. And then in particular, as part of the proof, we have a so-called Poincaré type inequality, which is the following. So the L2 norm of some form U here with respect to the conic metric and the singular metric on L is bounded by its D bar, provided that U is a form of this type, 0Q, which is in the domain of D bar, meaning that those D bar U square and U square is L2, and orthogonal to the space of closed 0Q forms. Okay, so this is the analog of Poincare inequality in our situation. And then one more notion that comes into the picture is the so-called current with the values in this singular Hermitian line bounded.
Sorry,
So,
Mihai, what is X naught before in the previous slide?
Oh, I'm sorry. This is a misprint. The X naught is X.
Oh, okay.
So I'm sorry. So what I was about to say is that now, of course, we have the notion of the current with values in a line bundle or vector bundle, but here we need again to take into account the fact that to take into account the metric, and then we cook up this notion saying that our current will take values in this L endowed with the metric HL, provided that when we couple L with the star phi bar of the star bar of some form which is smooth in conic sense like that, is bounded by a certain number of derivatives of phi. Okay, so when phi L is smooth, then this is exactly the notion of current with values in a boundary. But then if not, that's the complete, the perfect analog. And as an example, any PQ form with log poles can be formally written, has this property that when we couple it with this, then we can bound the integral by a certain number of derivatives of the test form. And then, so the important thing here to realize is that for this type of currents, we have the analog of the, if you want, de Rham-Kodaira theorem. That is to say, any such current can be decomposed as a harmonic path plus the Laplace of the green operator of this of the current T. Okay, if for example, if T is a PQ form, then this is right the usual decomposition in harmonic path plus the image of the Laplace. But then we can define this green operator acting on currents exactly as in the usual as in the non-twisted case. So this result was proved by de Rham and Kodaira if L is trivial in the absence of L, but then it has a perfect analog in this setting. So yeah, so this green current of T is defined by duality. So what's inside this result is the Hodge decomposition that I mentioned before. Okay, so I'm kind of running out of time, but okay, let's see. So let's see what does this has to do with what we want to prove. So when we look here at the equation that we have, remember that we have this logarithmic form is in the image of the d bar plus d prime. Now I can interpret this as a current, right? So well, first very easy reduction is that we can assume that alpha is 0 simply by since alpha has logarithmic poles, when we multiply with SE it becomes smooth. So I can move this term to the other side. So we only have this equation to deal with. Again, this holds pointwise in the complement of the divisor E. And then, so the statement that I would like to discuss next, which will solve this equation here, is the following: is that so if we have X endowed with this metric with conic singularities, together with a Hermitian line bundle and whose curvature verifies this, so we have as before a singular path, but we also allow a smooth path. Condition is that this is rational between 0 and 1, and theta L is semi-positive, and everything has simple normal crossing. And then now the equation that we can consider is the following. lambda, so divided by SE, exactly like here, it's in the image of the D prime plus theta wedge beta 2. So as compared to the equation we want to solve, this time lambda is an Q form with Q arbitrary, and we allow some part here. So if you remember here, the metric has no smooth part, it's just a divisorial. But if we have some smooth and semi-positive forms in the curvature are allowed, and then we can consider this sort of equation where the betas have logarithmic poles here, as explained here. And then, so if this equation holds in the complement of the singularities, then necessarily lambda is D bar exact. Okay, so it's like again, it's like a pushed generalized version of the usual DD bar lemma in host theory. So with the exception that here we allow some smooth and non-divisorial part here. Okay, so just a few comments about the proof. So here what we want to do is that this lambda is D bar exact. So then we will use the same ideas as in the usual L2 theory, trying to solve this equation lambda equal D bar of something by duality. So we consider a test form with compact support in the complement of the singularities, and such that values here. And then I can decompose my test form into two parts, one in the kernel of the D bar, the other one orthogonal to the kernel of the D bar. Well, the matrix here, it's so this one is given by the statement, and I take some smooth metric on E, so orthogonal refers to that. And then, so what is the heart of the matter here is to show that we have this orthogonality relation, so that this product here, it's exactly our lambda. So I want to show, if I want to show that lambda is in the image of the D bar, then beta be orthogonal to phi 1. So this is exactly what we prove. And for the phi 2, this one is orthogonal to the kernel of the D bar, and then we use Poincare inequality to show that it's smaller than this. So these two conditions, these two relations together will prove the theorem. The most important and subtle matter is to show this here, and this is where the decomposition of the currents in harmonic plus the image of the Laplace plays a role. Okay, so this is where the host theory and currents and all the disaster comes into the picture. Okay, so I will not detail any more. Just two things to remember. We use the duality and host theory in order to get this. Fine. So this one I already comment on it, and then so the theorem one is proved simply by applying this result. And now just a quick consequence of this DD bar lemma. And this is more for the algebraic geometers. So the statement is the following. So we have a compact Keller manifold together with a simple normal crossing divisor, and we also have a line boundary on X, such that endowed with a non-singular metric with semi-positive curvature. And we give ourselves a section of some multiple of F, but with the requirement that S is not identically zero on any stratum of the intersection, the components of this divisor E here. And then the conclusion is that the map, which is between these two spaces induced by S to the power M, is injective. Okay, so the map between the space of Q forms. NQ forms with values in E plus F, NQ forms with values in E plus N plus 1F. So this is given again by multiplying with S. For Q equal to 0, it's clear that it's injective, but maybe less clear if Q is at least 1. So that's the statement. It's injective for any Q. And again, so this is in connection with the extension theorem. This is a whole industry started with classical contribution by Tankeev and Collard, and then all these people did some contributions. These did important contributions, and if Osamu Fujino proved this if X is projective by using techniques from mixed Hodge theory, and then so those techniques, they don't go through in the Keller case, but so we came up with a proof as follows. Now, if I will only comment this case in which S is a smooth hypersurface, S equals to 0 is a smooth hypersurface, and then the hypothesis is simply that the zero set of S, which is Y, plus our divisor is a simple normal crossing. And then if we give ourselves NQ form such that when multiplied with S is D bar exact, the conclusion should be that lambda itself is D bar exact. So let's see how we do that. Well, we divide by S, right? And then lambda divided by SE will be exactly D bar of this in the complement of E plus Y. But then, of course, we are not we are not really advanced with this because we took the D bar in the complement of Y. And then what we will do is to somehow perturb the metric of F like this by adding a singular term. And then this somehow allows us to modify this equation. So because of the metric, because of this additional singularity here, we can write D bar of the alpha divided by this holomorphic section as D bar of theta plus some form in the image of the D prime and theta, when this time theta, as opposed to this one, has only log poles along E. So this is what we gain by this operation, right? Again, the method is as before by using an appropriate vector field and contraction and so forth, but the singular part here is essential. And then, now all that we have to do is simply to realize that we rewrite the equation like this. That's exactly the shape of the which is required by the previous results, the DD bar lemma, and we use that term 6 to conclude that this one here up, the numerator here is D bar exact. And then thank you for your patience and apologize because I ran over time. Yeah, thank you.
Mihai, on t'a pas entendu.
I said thank you, I'm done. Thank you very much.
Any other questions or remarks?
I have a question. Maybe so the Hodge theory part of the proof, it seems to me that it should also work in the context of higher rank bundles and consingularities. So do you know if similar extension results have been studied for higher rank bundles?
I don't know. It would be very, very important, very interesting to see. But then you have to. So this. Let me get back. In just a second. I don't know what happened here. Oh, that's the trouble with the technique. It's always crashes at the wrong moment. Wait. Let's see now here. let me get back to the host story. So here, what really matters for us is that well, somehow the singularities of the metric and the singularities of this HL, they are correlated, and then we can use local uniformization to.
Interruption d'Internet actuelle.
Excuse me?
Donc, on n'a pas entendu ça. L'Internet n'est pas stable.
Hein?
Tu peux répéter, Mihai, ta réponse, s'il te plaît?
Yeah. So what I wanted to say is that one reason for which this works is that we can somehow basically get rid of the singularities and of the metric and of the line boundary when we take these ramified covers. And so in case you have a vector boundary, you have to the situation probably much more subtle at this level, but maybe it works. But you have to give a very precise conditions here about the metric. What sort of singularities will you allow?
And the angles of the conic metric are of the type 1/m, no?
So somehow for the conic metrics, this probably is okay as it is, but then if you want to replace L with a vector boundary, so then the metric would not be just given by a weight, but by a whole matrix, and then you have many components there, and you have to somehow work a little bit more. I have no idea if such a result can be proved at least not with what we did. It requires some new techniques, I guess.
Okay, thank you.
I have a general question, Mihai.
Mm-hmm.
Everything went by very fast. In the beginning, you assumed L is -1 times K.
Yes.
Then I think the only hypothesis you need for L is semi-positive, right? Semi-positive singular metric.
Yes.
For the Hodge decomposition, I think that's the only hypothesis you need for this theorem.
So if you take L again, you take L minus K. Yes, and then as soon as you have the singular, as soon as the metric is given by some SNC, so some divisor which is so with rational coefficients plus some smooth part, this holds.
So you need L to be ample.
No.
Yes, you need S and C divisors. Okay, it doesn't have to be ample, but you know.
No. So all that you need is that the components are transversal. It doesn't need to be ample.
But in general, it's very difficult to guarantee that the components of sections.
Precisely. So, so this is why you take this resolution at some point. So in general, of course, this divisor is very complicating. We understand nothing about it, but luckily the L2 conditions and everything translates very well when we take this resolution.
Okay.
That's somehow the idea with it.
So the Hodge decomposition only works with the normal crossing hypothesis, because
at least
L2 condition is nice, so you can do it for after blow up.
Precisely. So I mean in this SNC, it's not so complicated to get it, but then I'm sure that with a little bit more work, one could get more general versions. because what you need is you know the usual Poincare type inequalities and this and that. Usually you get those by I mean, we compute integrals. Those are nice enough to, when you take resolutions and so on. So there is a chance that one can extract a much more general result, but we were just happy with what we've got. So that's it.
I guess if you assume L to be semi-ample, then this Hodge decomposition would work.
Oh, I guess so. Yes. I mean, in that case, you just take a metric which is semi-positive, smooth, and then the usual Hodge decomposition does the job.
Yeah.
Can we say something if we restrict the dimension to 2, for instance? In lower dimension, is it possible to say something extra?
In small dimensions, I hate these questions. Yes, I think that, wait a second. I think that the
Surfaces.
I don't know, but I'm sure that one can get the full conjecture in dimension 2.
Really?
But for wrong reasons, in the sense that you have a classification, you can use that. So what I mean is that so let's say it like this. In general, I mean, the main goal of this whole story was to attack this conjecture by Seaway, extension of pluricanonical forms. And then if the dimension is 2, then the manifolds which are there, well, they have canonical, which is pseudo effective. So basically, they are well understood, even in the Keller case. So this is why you can say more in this setting, but unfortunately not because of these methods that I presented here today.
Okay, very good. Are there any extra questions? Yes.
Yeah. So I have some general question. Can I ask, please?
Sure.
Yeah. So, for example, if we look in your basic 1 slide.
Yes.
So we can conclude that Su conjecture is true for m equal to 1, right?
Yes.
Okay. Okay. Another question. So if we look in Osawa-Takiguchi extension theorem,
yes,
can we formulate this more generally? For example, because you assume that the multiplier ideal shift is trivial by the second condition, right?
No. You mean this one?
Yes. And this implies
No.
that
The assumption is that U belongs to the multiplier ideal shift.
okay. So okay, yeah, you're right. So if you replace this condition by so for example, you take U, a section for Kx plus L times the multiplier ideal shift, and we skip the second condition. So the theorem will be true, I think.
No. So if you assume that the section is in K plus L twisted with multiplier ideal shift, that's exactly this. It's equivalent.
Yes,
right?
so we can skip this condition.
Well, you skip it from here, but you put it here. So what do you mean?
Okay. And the first condition means that the line bundle is pseudo-effective, right?
Right, exactly. Okay. That's right. So I mean, that's exactly well. The general comment here is that you have some conditions about L, right? And you derive conclusions about canonical plus L. So canonical boundary here is somehow curvature free, if you want. All right, like in all the theorems in complex geometry, that's somehow the prototype. some positivity conditional on L plus L2, and then you derive some conclusion about K plus L. So this is somehow what's behind these pluricanonical extensions. Is that you can add a copy of the canonical for free, so to speak. Okay, that's the important thing.
Okay.
But then, if you don't have any line bundle which is ample on the family, then you cannot apply this technique. So somehow,
Yes.
And it's
So
really
also for example, so the family here is from X to an open disk, right? So if this family is like algebraic morphism with connected fiber, so from projective varieties to projective varieties, so there is no pseudo conjecture because the push forward is always locally free, right?
No. So there are two things. I mean, here also the same results are true. So the pullback, the direct image of well, it's at least so what I'm trying to say is that extension of some section defined on a special fiber, and the fact that the direct image is torsion free, and since here we are on a disk is locally free, is not equivalent, right?
But if the family is smooth, the push forward is locally free.
Yes.
No?
Yes, but this is not equivalent to the fact that any section extends.
But it's equivalent to say that the plurigena is constant.
No.
No?
No.
Why? Because we take.
Well, so look, when you say that the direct image is locally free, what does it mean? It means that that you look. I mean, the fiber of this direct image is the sections which live in a neighborhood of that point, if you want. So somehow they are locally already extended.
But the rank is constant.
Yes, that's what I'm saying. But the rank is computed at a generic point, if you want.
Okay.
So again, when you take the direct image of some line boundary, let's say L, take P star of L. What does it mean that this is a line? This is a vector bundle on the base. You look, the objects that you are considering are sections of L which are already extended locally near that point.
Mm-hmm.
Okay. So, and in Siu's conjecture, you have to start with a section which only lives on a fiber.
I see. Okay.
That's the difference.
Okay. Thanks.
Yeah, sure.
Also, I know that your collaborator proved a Daka conjecture for when the base is of maximal Albanese dimension. So using the same techniques, extension, Osawa Takiguchi extension techniques. So can you say something? For example, if the family, for example, is of maximal Albanese dimension, it means that the fiber are varieties with maximal Albanese dimension or things like that.
Yes.
No, I cannot say anything about that. Somehow, my only intervention there was the paper with Junian, and then I moved to something else because if the base, I mean, in the case that you mentioned, for example, if the base was a tori, what really matters is that when you look at some well, there is basically two cases to consider where the determinant of the direct image is trivial or is ample, and there's nothing in between. And other than that, seems to me a very difficult problem. Yeah, so I don't know.
Thank you.